let's go over your roller coaster physics lab. So, for the prior knowledge questions, I included those answers on your class kick. You should have already gone over them as well as the warm up, okay? Those are expected for you to have already read through and understand. I'm going to pick up here on activity A, which on your class kick is slide 3, okay? I'm going to go through slides 3, 4, 5, 6, 7, 8, and then I will stop at slide 9, leaving activity C for you and your group. So please open up your class kick and follow along with me as I do the roller coaster physics lab, which is on Gizmos, as well as the answers to the lab report that I am revealing now. So for this activity, you need to get your gizmo ready, resetting all of the settings to a 35-gram toy car. So go to your gizmo, make sure you have the 35-gram toy car selected, and that hill 1 is at 100 centimeters. My bad, you guys, 100 centimeters. Hill 2, you're going to leave at 0 centimeters, and hill 3, 0 centimeters, making sure the coefficient of friction is also set to 0, meaning there's no friction. So here we go, 100, 0, 0, 0. Awesome, the gizmo is set up and ready to go. Now you may press play, record the speed of the car. Pressing play. Here is where the speed and the time are being recorded. 442.9 centimeters squared. So you come back over here, record that, 442.9 centimeters squared. Go ahead and try the other cars as well. So reset, put the 50-gram car, play it. Bonk, breaks the egg. The speed is still the same though, 442.9. Reset it, you can do it with a 100-gram toy bus, a little VW bus for my Beatles lovers out there. Still, speed is 442.9 centimeters squared. Coming back over to our lab, the question, part B of question 1, other cars, does the mass of the car affect the speed? No. No matter the mass of the car we selected, we ended up with the same speed. So the whole point, as I keep going, everyone, here, the lab report is asking you questions that lead you directly to the answer. Just by following the instructions and copying your answers, you are coming to the answer for the lab, okay? So with just this beginning experiment that we ran, we know that the mass of the car is not mattering to us today in this lab, okay? When we're focusing on gravitational potential energy and kinetic energy of the hill and breaking the egg, the mass of the car is not mattering so far. So now we're going to use the 35-gram toy car. I know that was a confusion for some of us. And we're going to find the speed of the toy car, okay? So we're going to set it up as whatever in this table delineates. So hill 1, 40, hill 2, 0, hill 3, 0. 35-gram car, 40, 0, 0. Double check, 40, 0, 0. What's my final speed going to be there? 280.1. So you would record 280.1 on the final speed. Also for you guys, it said leave last column blank. That's this one right there. Total height lost. That you don't know. That was not included on your class kick, but obviously my sheet here has all the answers. So you would record the speed. Then you'd repeat that process again and again and again, keeping the toy car at 35, not that it matters which one you use, and adjusting the differing hills, okay? Then we come to analyze. Look at the data carefully. Notice that it is organized into 2 sets of 3. See this little split right there? There's this set of 3 where they all have 280.1 centimeters per second as the final speed. And then there's these 3 that have 343.1 centimeters per second as the final speed. So did hill 2 affect the trials at all? No, because the speeds were the same no matter what in the first three and then the second three. So looking at the data, what was the correlation there? It was the total height lost, because the first three, regardless of hill 1, hill 2, they had the same amount of height lost. Same thing going on here for the second set of three. They have different hills 1, different hills 2, but the total height lost was the same for those three, and they ended with the same speed. That leads us to the conclusion that the total height lost was the same, and the only factor that affects final speed is the total height lost. I'm going to give you guys a second to check your graph for 2, as well as what conclusion you came to here. So now we know the mass of the car doesn't really matter, but what is mattering is the total height lost in terms of determining the final speed. I can also pause the video here for a minute. Okay, activity B. Now that we have that under our belt, we're going to reset to the 50-gram car. Coefficient of friction is 0. Set hill 1 to 100, hill 2 and 3 to 0. So let's go change our gizmo. We are going to reset it, do 50, 100, 0, and 0. You're going to click the graph to be showing and then select E versus T. So when we click show graph, we have a lot of options here. So dependent on what you're looking for is what you'll click. So E versus T is energy versus time. And that's not a specific energy as in kinetic energy or gravitational potential energy. It's just all of the energy within the system versus the time as the car runs. We do have those options though for gravitational potential energy represented by a U, or kinetic energy represented by a K. Both those have a J next to them because the units they're using in energy is joules, Joules. So there are lots of options there. We're just going straight forward for energy, all of it. Okay, when we press play there, what is the energy doing as that car goes down the hill and then across the bottom flat spot? Here in the graph we see the energy is the same for time. There's no increase or decrease. It is entirely the same. So we go and record that. Does the total energy of the car change as it goes down the hill? No, it stays the same. Now we're going to check out the gravitational potential energy of the car. So we're going to go to the U versus T graph. So we're going to reset it. We're going to go U versus T and press play. Here we see that it starts at that same point, but as it goes down the hill, it also loses that energy over time. So gravitational potential energy goes down. So what happens to it as it goes down the hill? It decreases. And then, oopsies, Miss Birch made a mistake. We're going to set hill 3 to 99 centimeters. So we're going to reset that because I missed that part. Hill 3 is going to go to 99. And we're going to watch that graph again. So as it goes down the hill, it loses its energy. As it goes up the hill, it gains potential energy because, again, it has that potential to roll back down and gain kinetic energy. So decreases as it goes down the hill, it increases in potential energy as it goes up the hill. Now we're going to do the same thing for kinetic energy. So leaving my graph as is, resetting, going to K versus T. Pressing play, watching that go. It's an opposite graph. At first it starts with no energy. As it goes down the hill, it gains kinetic energy, stays the same, and then loses the kinetic energy as it goes up the hill. So it's opposite there. Increases, decreases. 4, compare. We're going to reset our graph once again. We're going to set hill 1 to 80, hill 2 to 60, hill 3 to 79. 80, 60, 79. 80, 60, 79. And I believe coefficient of 0 is still 0. 50-gram car, press play, and then we're going to look at all those different graphs again. So I'm going to leave it here on the K graph, and it looks like that. You can take a screenshot, add it to your report. So same graph there. Let's go check out the U. It's going to be opposite. In this case, it makes a W kind of format versus an M here. So you'd screenshot, add your graph. And again, in your class kick, your guys' is blank. Okay? So you do need to add, whether you sketch it on there or add a screenshot, that is your choice. But you'll want to add it. And then lastly, resetting and doing it for energy. It's a flat line. So then, now that you have these, we're going to draw the conclusion. And the conclusion of how are PE, KE, and TE related is as follows. I'll let you guys read that, and then in class I'm going to do the actual mathematical equations for gravitational potential energy and kinetic energy in class with y'all.